Okay, so for this one, it was a question of, here was the prompt. The computer did take this answer, but then when you check the key, it shows that answer. So let me show you how you get from here to here. So this is that property where we have, if we have a root of a couple of things multiplying, we can think of that as two separate roots, or vice versa, depending on which form is maybe more convenient for us in that moment. The other thing we have is the idea that if we have a perfect square going on underneath a radical, so for instance, if I had the square root of 12, 12 is the same thing as the square root of 4 times 3, and square root of 4 is a perfect square, so I can rewrite that as square root of 4 times square root of 3, and then we got 2 root 3. So that's the same thing we're doing up here. With the 12, it's a little bit easier to spot the 4. 48 is slightly sneaky. So for 48, you might spot the 4, but it's really 16 and 3. So it's the biggest perfect square that divides in there. And that one, like I said, is slightly sneaky. So 16 times 3 does make 48, and square root of 16, that's a perfect square. So I can bring that out front. And then I have I times 4 root 3, and then they wrote it in the other direction just because this is the B and the I. So the I should really be on the other end. In terms of trying to simplify radicals, it helps to realize that there's a really limited number of numbers that you can work with. So 2 squared would be 4, 3 squared would be 9, 4 squared would be 16, 5 squared would be 25. Right there, 25 is already too big to divide into 48, so it's not that. 9 doesn't go into 48, so it's not that perfect square. 4 goes in, but then if you tried 16, it would go in as well. So that's what you can simplify out. But basically, if you hadn't found any of these numbers, like let's say we had 35, square root 35, 4 doesn't go in, 9 doesn't go in, 16 doesn't go in, it doesn't simplify. It's a 5 times a 7. There's nothing that you can reduce out of there. Cool. Hopefully that helps.